Ever wondered how a robot can slow down smoothly before stopping? In this demo, watch how the mBot2 reacts as it gets closer to an object. Let's visualize what's going on with a graph. Welcome back to Learn as You Explore, your go-to place for mBot2 tutorials. If you are new here, I'm a robotics software engineer who loves helping students learn robotics and supporting teachers who teach it. Today, we're diving into linear interpolation, a fancy name for figuring out values in between 2 points and using it to make our robot slow down smartly and smoothly. Quick note, if you're excited to grab the mBot2 or any accessories, check out the links in the description. I've added Amazon and Makeblock links. If you use the links, I may earn a commission at no extra cost to you. Thanks for supporting the channel. So what is linear interpolation? Let's say we want our robot to slow down gradually as it gets closer to an obstacle. We know two important points. When the robot is 30 centimeters away, it should move at a speed of 50 RPM, and when it's 5 centimeters away, it should be completely stopped. That is 0 RPM speed. But what if our robot is at 20 centimeters? What should the speed be? That's where linear interpolation helps us. It's just a way to find values between two known points when they're changing at a steady rate, like drawing a straight line between them. Once we have such a line, we can easily find out what speed the robot should be driving at when it is at a given distance away from the obstacle. In this case, at 20 centimeters away from the obstacle, we can find the point on the line corresponding to the value of 20 centimeters and infer that the robot should be driving at a speed of 30 RPM. To do this mathematically, so that we can implement that math in code, let's break this down in two ways. First, we'll walk through an intuitive explanation, and then we'll look at the math equations for students who've seen the slope-intercept form of the line equation. From 30 centimeters to 5 centimeters, the speed changes from 50 RPM to 0 RPM. That's a drop of 50 RPM over 25 centimeters. This means that for every 1 centimeter closer, the robot slows down by 50 over 25 equals 2 RPM per centimeter. This is our rate of change, or slope. This tells us that for every centimeter that the robot moves closer to the obstacle, its speed reduces by 2 RPM. So if the speed reduces by 2 RPM per centimeter, how much should it drop when we move 5 centimeters? That is simply 2 times 5, which is 10 RPM for every 5 centimeters. So if we make a table showing the distance away from the obstacle and the corresponding speed that the robot should be at, we can clearly see that as the distance drops every 5 centimeters, the speed drops by 10 RPM each time. This shows a linear relationship between the distance and speed. If you've seen the slope-intercept form, you can also write this as a math equation. Speed equals slope times distance plus intercept. Y equals mx plus b is the slope-intercept form. Here, our y is the same as speed because speed is in our y-axis in the graph. And x corresponds to distance since distance is in our x-axis. M is the slope and b is the y-intercept. We already figured out the slope in the previous slide, which was 2 RPM per centimeter. Now let's plug in a point to find the intercept. Let's use 30, 50. So x is 30, y is 50, the slope m is 2, and the intercept is what we want to find out. So that can be easily done by simply rearranging the terms, and we find that the intercept is -10. So our final equation is speed equals 2 times distance minus 10. And this is a general formula to find the speed for a given distance, given our linear relationship that we have modeled and designed as shown in the graph in the previous slide. Now let's test it out. We have our final equation, and we previously determined 3 different distances and the corresponding speeds from the graph. Let's see if the resulting speed from our equation matches up with what we had previously calculated. First, at 30 centimeters, our speed is 2 times the distance, which is 30 centimeters, minus 10. So that is 50 RPM, and that matches what we previously saw. Next, at 5 centimeters, our speed will be 2 times 5 minus 10, which is 0 RPM, and that also matches. Finally, at 20 centimeters, our speed is 2 times 20 minus 10, which equals 30 RPM, and once again we have a match. Great! It works perfectly and gives us smooth, gradual slowing as the robot gets closer to the obstacle. Whether you're thinking about it visually or mathematically, linear interpolation lets you find the just right speed between two known points. Now let's use it in code. Here's the plan. We'll use the ultrasonic sensor to keep checking how far the robot is from an object. If the object is more than 30 centimeters away, we will drive at 50 RPM. If it's less than 5 centimeters away, we will drive at 0 RPM, which is essentially stopping the robot. And finally, if it's between 5 and 30 centimeters, then we will calculate the speed using linear interpolation. Hey there, if you're a teacher and want to use these slides in your classroom, plus get a full lesson plan, printable worksheets, and starter code, I've put everything together in a ready-to-use premium lesson pack. You can grab it using the link in the description. I have the basic structure of the program done here. As always, we have our decorator for the button B press, and we have our function attached to the decorator. We have 4 variables here. We have the max distance, max speed, and min speed, each of which should be self-explanatory. We know from our slides and from our flowchart that the max distance is 30 centimeters. The min distance is 5 centimeters, the max speed is 50 RPM, and the min speed is 0 RPM. We have our while loop that helps us exit the program when button A is pressed. The first thing we'll do within the loop is we'll get the distance from the ultrasonic sensor. Now we have to implement our core logic. This comment block captures what we had in our flowchart, so it is a good reference for implementing the logic here. The first thing we'll do is we'll check if the distance reported was greater than the max distance. And if it was greater than the max distance, we want the robot to drive forward at max speed. So we'll use the mBot2.forward API and give it the max speed as the argument. We will also log this to the CyberPy display using the CyberPy console println function. We will just say max speed here. Else, if the distance was less than min distance, the robot will move forward with min speed. We will also log this to the CyberPy console, and we'll just say min speed for the log message. Finally, we'll have an else block here, and this captures the case when the distance is not greater than the max distance and also not greater than the min distance, which means it's between the min and max distances. This is when we want to linearly interpolate to find the correct speed along the line. From the equations that we derived in the slides, we have the interpolated speed is 2 times distance minus 10. This is because 2 was the slope that we found, and negative 10 was the intercept, and this entire equation is just the equation of a line in slope-intercept form. Now that we've calculated the interpolated speed, let's log it to the CyberPy console. The CyberPy console println API always takes a string, whereas the interpolated speed is a number, so we want to convert that number into a string. In addition, I'm going to make sure that the interpolated speed is an integer. And here we can also concatenate, which is simply saying that you can join two strings together so that we see the number space RPM on the display as the robot prints the interpolated speed. Once again, we'll use the mBot2.forward API and pass in the interpolated speed this time. Let's save our program. And we're done. Let's upload the program to our robot to test it out. Click Connect, select the COM port, and click Connect again. Select Upload Code and wait for the code to be uploaded. Let's head on over to the robot to test it out. If you've made it this far in the video, please consider giving the video a thumbs up by clicking the like button and subscribe to the channel if you haven't already done so. It really helps keep the channel going. Pressing button B, the robot drives forward and slowly decelerates as it approaches the obstacle and stops completely at 5 centimeters away from the obstacle. Here are some of my other videos that you may find helpful. Happy programming, and I'll see you in the next one.